In this segment, I'm going to talk about the new tool that we've introduced to model electric interactions, namely the electric field. And so we'll go over what an electric field is, how we can calculate it, how we represent it visually and symbolically, and finally, what is its connection with the electric potential. Okay, so first off, uh, the electric field is a vector field. Okay, and so what does that mean? Well, if you recall, for when we had introduced a scalar field, like the electric potential is a scalar field, then a scalar field is simply something where for every point in space, we associate a number. Okay, so similarly, a vector field is something where for every point in space, so in every xy coordinate, we associate a vector instead of a number. So that's a vector field. Okay, so for a single point particle, this is what the electric field looks like. Okay, so we denote it by the capital E, and it's a vector, so it's E vector. And as usual, we have the Coulomb constant Kc, the charge of the point particle. R here represents the distance of that point particle. So the distance of uh, the point particle from a particular um, field, from a particular point or xy coordinate. So and as usual, our hat is the unit vector. Okay, so that's how we define the electric field for a single point particle. But let's try to understand how we can go about calculating an electric field and also how we can represent it. Okay, so you'll first start off with a simple example, and that example is of a vector field of a single point particle placed at the origin. Okay, so, and we're only going to look at the positive x-axis. So suppose this direction is my positive x direction. The origin is right on top of the particle. So then we're going to ask ourselves the question, what is the electric field maybe at this point and this point, and eventually try to figure out what it looks like for all points along this horizontal line. Okay, and then you can also repeat it for the other side as well. And then later on we'll go to a more complicated example of 2 dimensions and ask what does the electric field look like as I go along that direction or that direction, or any of these directions on this plane. Okay, so let's start off with this one. This point over here is a distance of 2 from the charge, right? So 2 units of distance from here, 1, 2, and so r is equal to 2. Okay, and so this is the strength of the electric field is Kc q by 2 squared. Okay, which is nothing but Kc q over 4. Now there's also a vector associated with it, but for 1 dimensions this is straightforward. We already know that what that vector is. The vector is simply pointing along the x direction, so it's just x hat. Or in other words, if I try to draw some kind of vector qualitatively representing this, what I have written down here, then I would draw a vector out maybe like that. Okay, because it's pointing away, so r hat points away. You're standing on top of plus q and looking at that point, so r hat points away from this, from here. Now similarly, let's try to look at what this point looks like. So this is now a distance of 4 away. So similarly, this is Kc q by 4 squared x hat, and so that is nothing but 16 Kc q over 16, which is 1/4 of what this is. So this, when I try to draw out a vector at this point, I would draw it as a smaller arrow. In fact, if it's possible, I try to keep it like maybe 1/4 the length of the original of the arrow that I drew originally, so that this arrow should be about roughly 1/4 the length of this arrow, because that's what I see over here. Similarly, I can carry on. Let's say if I looked at this point here, then this is going to be KCQ over 64, because this is, oh sorry, KC, so this is now 246 away, so this is going to be KCQ over 36, KCQ over 36, and so this is going to be an even smaller arrow, and so on and so forth. Okay, and I can repeat this exercise on the other side. So along this direction, I have again KCQ over 4, but this time around I am looking at the negative x direction, so it's going to be a minus x hat, or I can just put the minus out there, and so this becomes a minus KCQ over x hat. And so if I draw an arrow, it's going to be an arrow that is of equal length as this one. Maybe I didn't draw it out properly. So it's going to be of equal length as this one over here, but pointing in the opposite direction. And I can keep going on. There will be repeated arrows pointing along in that direction. And in principle, I should be doing this for all points, or even these points in between. But the figure gets messy, so we won't do that. And in fact, because it's hard to keep track of the arrows can be overlapping each other a lot. So instead, what we will do is to introduce a new visual representation called electric field lines, motivated by what we see over here. So instead of now drawing arrows at each individual point like this, right? If I repeat that, so drawing individual arrows on each of these, what I will do is I will actually connect all the arrows in the directions they point in and create just one single line and leave on them just the direction, right? So similarly on the other side, I will connect all the arrows that I could draw, and I will just draw it as indicated by one line, and on that line I will indicate the direction in which all the arrows are pointing. Okay, so now let's go over how this is all related to the electric potential. Well, if you recall, just like the force is given by the derivative of the electric of the energy, the electric field is also related to the electric potential V through a derivative. Now notice I've written out these r hats over here because these are actually vectors. We are usually used to doing this in one dimension, and so we usually just drop out the vectors from there, but we are going to be dealing with two dimensions, and so we include this vector over here. This is just an aside. It's not so important to know, but just so that you know, this is not the most general way of writing down the vector equation. There's also the x and y components, or theta components, but that's not so important to know. This is just, it's important to know that this is enough for at least point particles that we're writing down, that we're going to be dealing with. So let's come to that. If you remember, if I am looking again, I'm still looking at the same problem. I'm looking at the electric field and electric potential due to a single charge, and I'm looking along the x direction. So this is what the potential looks like as I plot on the y-axis the value of the potential, and along the x-axis, I'm plotting the x-axis is the coordinate axis, and y-axis is the value of the potential. So as I come closer to the charge particle which is located here at the origin, the value of the potential increases from either end. Okay, so if I now look at the slope of this, and remember that the form of the potential is kcq over r, right? And if you do some calculus, you will see that dvdr or minus dvdr is nothing but kcq over r squared, which looks exactly like the at least the strength of the electric potential, okay, or the magnitude of the electric potential. So, if I wanted to look at the slope, say at this particular point, here, well, this has some. How do I look at the slope? I draw a tangent line along that. This has some slope, and let's compare that to the slope along this line, say, along the line or point over here, and this has a much smaller slope. So this is some large negative slope. This one here is some large negative slope. This one here is some smaller negative slope. And so here the electric field is going to be large, so large electric field. And this is going to be a smaller electric field. And the electric field, as usual, is just going to point away from the origin, right? Another nice way of thinking about this is to say, ask the following question, that if this is the potential and I were to place a say a ball over there, which direction would it roll in? It would roll in this direction. Okay, so it's moving away from the axis. So the electric field also, you can ask a similar question, which is, if I place a small test charge particle over here, which direction would it move in? And so it moves away from the origin, right? And so the electric field lines, I know, are going to be pointing away from the origin in either case, right? Also, the other thing I can ask is, if I had placed a ball over here, then where is the acceleration largest? Well, the acceleration is large over here, but it's going to be smaller over here. And so the same analogy applies here. That is, the electric field is going to be large over here, but all the way out here, the electric field is just going to be small. So it's much larger here, but it's going to be much smaller there. Okay, so these are just ways of trying to visualize and understand what's going on. Okay. All right, so let's come to a more complicated example of a point particle, but this time we're going to map out what the electric field looks like in 2 dimensions. Okay, so let's start with this point over here, because you've already done this. So as usual, this is kc q over at the distance of 2 away, so 4, and it's going to be pointing away from the charge, so that's some arrow, let me represent it by that. And this one is going to be, say, kcq over 16, and so this is some x hat. So it's pointing away from along the x-axis, and this is kcq over 16 x hat, and so it's going to be a smaller arrow pointing away. And similarly for this side, this is kcq over 4, but there's a minus sign because now the arrow is going to be pointing away towards the negative x direction, and similarly over there. And now we can ask, okay, what's happening along the y direction? Well, along the y direction, you have the same thing. So this is going to be, the magnitude is the same, kcq over 4 over here. This is going to be kcq over 16. 16, and so that points away over there. Just for sake of completeness, let me actually represent it as a proper vector. So then this point over here, let's ask the question that this is, okay, 2 in the it's 2 units in the x-axis, along the x-axis, and 2 units along the y-axis. So in fact, if you calculate r hat, it is simply, for this point, it is simply 1 by square root of 2, 1 and 1. And let me write that out in a little slightly differently. So that's just 1 by square root 2 x component and 1 by square root 2 y component. So that's r hat. And so now I'm going to multiply r hat with the electric field. So that's kc q over now the distance. The distance is square root 2, and so the distance is 1 squared plus 1 squared, and square root of that, so that's square root of 2, and so that is just going to be this square root of 2 squared, so which is just simply 2. Okay, and so then this is really pointing to a vector that is somewhere there. It's pointing away, and as I move further away, this vector reduces in magnitude. Okay, so now we can just do this conceptually. The same thing is going to happen over here. This is some electric field that's pointing away from there, but as I move away, further away from the charge, the strength of that electric interaction is going to reduce. You can keep doing this for all other points around, and you will see that it's in fact a nice, as this takes on this nice symmetric shape. And so then that's what the electric field roughly looks like. So it's just a lot of arrows pointing away from the charge of interest. Okay, and so then how do you draw the electric field lines? Well, you simply connect all these arrows. So I would connect all these arrows in this way. I would connect all these arrows this way. Similarly, connect all these arrows and these arrows, and just indicate the directions for all these electric field lines. Okay, so that's the representation we're using, electric field lines. And so in purple, I'm showing you how I would draw out the let's skip that a bit, electric field lines. Okay. So now let's come to the connection of let's ask the question, like, okay, there is a connection between electric field and electric potential, so there must be some relation that I have between electric field lines, okay, the representation of electric field lines, and the representation of equipotential lines. So if I come to this figure and you remember what this looks like, this was the equipotential lines that we drew for a single point charge, and really this is a way of representing some kind of shape of I guess a mountain as such, as concentric circles like that. So these are lines of equal height or lines of equal potential, so equipotential lines, and we are and so when you look at this from the top down view, then this looks like these nice concentric circles. So if I copy this figure out here, so if I copy the figure that I've drawn here onto this for the electric field lines, then I end up with electric field lines that, well, I'm just going to draw them, a few of them. And I end up with electric field lines, and remember to always indicate the direction. Electric field lines that look like this. Okay, so in the figure for plotting for the equipotential, we see that there are more circles, or the density of circles is much higher closer to the charge, but as I move away, the density of equipotential lines is a lot smaller. Okay, so what does that represent? That really represents that a more rapidly changing equipotential line, right? Equipotential surface. So if I had a over here, for example, close to the charge, the potential is rapidly changing, and so I have more equipotential lines, and further away it's not as changing as rapidly, and it's much flatter, and so there's much more spread out. Similarly, the density of electric field lines, where are the electric field lines more dense? There are more electric field lines close to this charge, but as I move away, the distance from these electric field lines, they have increased, right? The separation between these electric field lines are increased. They're not as dense, and that again represents the density of electric field lines means a higher density of electric field lines means a higher electric field strength. So in class, we will explore more of these properties of electric fields, and we'll try to study different charge systems and understand all the different properties not only at both at the conceptual level and also at in much more depth.